As always, I want to say thank you to Patrick JMT, Integral Calc Curl, and Sal Khan. This video is about Bernoulli equations. But before we do that, here's something completely random and helpful. Did you know that the integral of u sine u du equals sine u minus u cosine u plus c? It's also the only integral you'll find on this particular banana. So here's like how I remember that. Just think, if you can memorize all these lyrics to songs you like, then you can memorize anything really. But watch this. Okay, so I remember the blue one first, but it always goes, so u sine u du, okay? This is kind of the sine u guy, this is the kind of the cosine guy. So it repeats itself, sine u, then it's minus u cosine u. Well, okay, see how they crisscross? So u cosine u starts with cosine u, and then it's just this. And then note that this is a minus sign, and this is plus, so I don't know. It's a good one to know. It has nothing to do with Bernoulli equation whatsoever. But some people have a knack for remembering extraneous information, and if you're that person, like me, you'll find that useful. So anyways, so here's our problem. Just to remind us, so this is the standard form for a linear differential equation right here, and here's a standard form for Bernoulli, and by inspection they're very similar. The only difference that's staring me in the face is that this one has a y to the nth term on it, so if we want to make a Bernoulli look like linear, it would make sense to divide out this y to the nth term, so it's exactly what we're going to do. So there's my nth term is -2, so I'm going to divide all sides by y to the -2. Of course, so division is a multiplication in the inverse. So that was -2, so I'm just going to multiply by y squared. Y squared times y to the first is y to the 1 plus 2, which is 3. And whenever I do that on this side, that will simplify to 1. Okay, so now I've got it like that. Alright. Conceptually, what the book says is let v equal y to the 1 minus n. And then actually, or I guess specifically, for us, our v is going to be, well, our n was -2, so 1 minus -2 would be 1 plus 2, so that's our v. It's going to be y cubed. So then the derivative of this v with respect to x, power rule, 3y, decrement the power by 1, and of course it's a chain rule, times whatever the derivative of y is with respect to x. Okay. It used to kind of trip me up I used to try to put this one, I guess, from the definition into my work. Some people just remember this long formula, but it's much easier for me to say let v equal y to the 1 minus n, and then see what that actually is, and then we derive from there and then substitute. So anyways, as you can see, this is very similar to this right here, except this factor of 3. So let me just pull that 3 out of here, and I can say that 1/3 dv dx is equal to exactly what we have in our problem. Alright, so let me just throw that over here. So instead of this, I'm going to write exactly what we said that was equivalent to. And I'm going for something that's all in v and x language. Alright, now plus y cubed, well, we said that was v. It's not quite in standard form of a linear equation yet. So this one starts with dy dx. Let me make this one start like that. Just multiply everything on the left hand side by 3 to break out that fraction. Whatever I do to the left hand side I have to do on the right hand side, else that equal sign would be a lie. Okay, cool. So now we're a linear equation. And like all linear equations, we're going to find a mu so that we can rescale everything. And mu is always going to be equal to e raised to the integral of px dx. I'm going to write this from here down, starting on a different sheet. Now I'll just push it up. Okay, cool. So 3 in this case is our p. All this, go back to here real quick. This px and this qx, they don't have to be functions of the independent variable. It could just be constants as well, and that's exactly this. I like to remember it as this derivative plus a function of the independent variable or constants times dependent variable equals just a function of independent variables or constants. So that way I don't get caught up, because what if it's a t or a theta or something? Anyways, okay, so let's see. This p is just 3, so the integral of 3 with respect to x is just going to be 3x. And didn't we say that this was e to that? So that's what our mu is just e to the 3x power. So let's multiply everything by this mu. And this I will do on a separate sheet. Alright, I know that the right hand side, so this is the same base. How long were you guys going to let me keep it that way? Alright, so same base, so e to the x times e to the 3x, just be like if I had x squared times x cubed giving me x to the 5th. In this case, e to the 4x. And the left hand side, kind of already know that it's going to be whatever mu times the dependent variable was by the definition of mu. So that was our mu, and that was our dependent variable. This is all just realizing this inherent product rule, but we can sit back and think about it and see if this in fact is a prime times b plus b prime times a. After a while you'll see that, yeah, it is. Cool. So if I integrate both sides, when I integrate a derivative of a function, I'm just going to get that function. Okay, so integrating e to the 4x. I pulled out that 3. Well, if I integrate e to the 4x, I'm just going to get e to the 4x over 4. I'll put that 3 back there. So plus e like that. Okay. Alright, so there I'm at right there. And I noticed that they both have these factors of e to the 3x in them. So I could divide by, that will go to just e to the x singular. So v equals 3 e to the x over 4 plus c. That would be wrong if I left it like that. I divided this side by e to the 3x, so I can't just not do that to this constant right here. Yeah, that's important. You always got to do math on your constants when you bring variables into the picture. Okay, so we said that earlier we had said that v was the same as y cubed, so let's put that y cubed back. Alright, I believe it. Alright, cool. And remember, don't forget, bam!